Ladies and gentlemen, hello and welcome to my presentation. I'm going to give you in the next few minutes some introduction into beam shaping in laser processing. My name is Michael Schmidt and I'm here for the LPT, the Institute of Photonic Technologies of FAU of the Friedrich Alexander University in Erlangen. Before starting with the topic, let me shortly introduce where I come from. So as I said, I'm coming from the Institute of Friedrich Alexander University, Erlangen, Nuremberg. And just let me shortly have a laser pointer here. I'm in the Department of Mechanical Engineering. As I already said, my name is Michael Schmidt. My institute has around 40 employees at the moment. Most of them are third-party funded, of course, and not paid by government. So the history in this university about lasers is, well, not a very long one, but still a quite long one, especially in the Department of Mechanical Engineering, where in 1982 the Institute of Manufacturing Technology was founded with Professor Geiger. He was mainly doing forming technology, but also a little bit of laser technology because he came from Trump company. In 1987, the first time some association on lasers in engineering was founded inside the university. And 1993, the Bayerisches Laserzentrum GmbH, so the Bavarian Laser Center, was founded as a company and continued until now, by the way. In the year 2000, roughly a little bit before and after, out of the Bavarian Laser Center, also two other companies were founded, which are still quite successful today. It's the Airless company and the Laser Equipment, which is a main part of LPKF AG at the moment. So I joined, by the way, in the year 2001, the Bavarian Laser Center. Since 2005, I'm heading the Bavarian Laser Center. In 2009, the university decided that they wanted to have an Institute of Photonic Technologies also inside the Department of Mechanical Engineering. So this new Institute of Photonic Technologies started, and I had the honor to really start it since then. And up to now, as I said, we are around 40 employees. So our turnover per year is roughly 4 million euro. What are the research fields of this institute? So our core center, doing own research work and serving all the other groups, is the simulation and the modeling group. Also the sensing, control and real-time systems group, of course, is doing its own research and serving the other groups like the additive manufacturing, the ultra short pulse laser technologies group and the photonics in medicine group. What I'm going to tell you today is a part of first research ideas and work from our additive manufacturing group. And with this, let's go into details starting now. Let us have a closer look now on the process of powder bed fusion of metals with lasers. As you can see in the lower right corner, this is the process as in a powder bed machine that you can buy today. To be honest, this is a little bit exaggerated because this is just the first line of melting, and if you then do the second line with a certain hedge distance, the spatters are less than it's shown here. But what I want to show you is that, I think you already see it, the process is really quite unstable. It's a very dynamic process in the molten pool, but also concerning spatters and also powder flying around. And what you definitely don't want in this process is having big spatters flying around and maybe landing somewhere else in the powder bed, where you later on, for example, want to also image your part, because then the agglomerated particle is much bigger than the normal powder particles and cannot be melted anymore by the line energy that you have, and then it's already pre-programmed that you have a defect there from your process in your part, and this is something definitely you don't want. So if you look at these processes today, the state-of-the-art processes, of course you would like to have an increased process stability and of course as always a building speed as high as possible. You might also like to be able to influence the temperature field that you cause with your laser and also influence the cooling rates by this to have less residual stresses in your part and maybe even be able to manipulate the microstructure, avoiding hot cracking or tuning the mechanical properties of your part. And the spatter reduction I just already mentioned, this is some of the really severe problems that we have at the time. So of course you can start at, let's say, many points to change this and to influence the process. What I'm going to talk today about is the intensity distribution. So influencing the laser beam shape is the topic. There's normally two ways. The first way is that you have a fast beam deflection, and the second way is that you change your intensity profile. Talking about the fast beam deflection, of course, if you can do this quick enough, like with wobbling or beam oscillation, we had in this context some presentations before, you influence the molten pool shape. But unfortunately, normally, interestingly, with our laser beam and the means that we have to influence the speed and the direction of the laser beam, we are not fast enough to have a simultaneous beam shaping. So that means the molten pool dynamics will always follow our beam trajectory that we have. By the way, if you would have an electron beam that you can deflect just using electric or electromagnetic fields, you can easily reach kilometers per second in arbitrary shape, and with this you would be able to have the molten pool not following your beam trajectory and having a simultaneous beam shaping, looking from the side of the powder bed at least. And this is something that a little bit I don't like, because we have the laser beam. This is a massless beam, and we are slower than an electron beam which has a mass. So this is something I think in future we need to do some research on. But what we can already do today is simultaneous beam shaping, as you can see here, for example. So having an adapted beam profile, not only the Gaussian or top hat intensity distribution, and by this also influencing the molten pool dynamics that we have. And which ways do we have to influence the beam shape? That's something you can see here on the left side. The first thing you think about is maybe choosing freeform optics, but there are some limitations due to the manufacturing process. A second thing you already can buy is diffractive optical elements, so static elements that work diffractive, and depending on the number of phase levels that you have better or worse efficiency or quality of your hologram that you produce with this. The picture you see here is something we did, and it's a binary hologram. That means this is from terms of efficiency not so well, but we can produce this quite quick, and as you see from the green lines around it, I'm going to focus on that in a moment. But before, let's discuss the two columns here on the right side. These are something like the gold standard we would like to have, because both of them, they allow an instantaneous dynamic beam shaping. So liquid crystal spatial light modulators are already out there in the field and are, let's say, used as state-of-the-art already with ultra-short pulse lasers. They are dynamic, nevertheless they are limited to 100 or at least a few hundred hertz in updating the shape. And they have some problems in handling higher power. So if you go beyond 250 watt mean power, you might have problems with the heat accumulating in the liquid crystal here. So note, I might speak about SLMs here, which is spatial light modulators, and the same shortcut SLM is also used for selective laser melting. So we have to pay attention here. A second thing that is at the moment under investigation, also in our institute here, is acousto-optical beam shaping. You can use these quartz crystals with sound waves in there to program, let's say, the diffraction of the beam that you bring in here, and you can use this for deflection as well as for intensity distribution change. Nevertheless, also here the efficiency is something that we have to look at. But we can go up in the dynamic range to megahertz, and also we can go up to kilohertz in the power range. So this is why it's a promising technology, maybe. There's a few others outside, but I'm not commenting those because they are at the moment not in a state where you really can use them. So our experiments I'm presenting today were done with such a type of DOE, with diffractive optical element, and we made it quite easy. We use an ITO layer, so indium tin oxide layer on a glass substrate that we bring there with a defined height on the glass substrate. Then we use ultra-short pulse laser ablation to make a pattern there, and the pattern is defined using a Gerchberg-Saxton iterative Fourier transformation algorithm that we calculated before. And then we use all this to shine our laser lights through the glass substrate, and where there are rests of the ITO layer, we get a pi phase shift, so our lambda half phase shift, And by this we have like a phase mask, allow phase modulation, and have a phase hologram to program a shape of our beam on the target plane that we want to have. So it's arbitrary. Nevertheless, of course, you cannot change it dynamically. If you have it once, then you need to use it. So this is quite a low-cost solution. It's fast to fabricate. It takes less than 2 minutes if everything's fine. But we only have a binary hologram, as you can see here, which is not so good for the efficiency. But we are quick, and for our preliminary tests that I'm going to show you next, this is a quite good thing. So we built this in, let's say, a laser head that we have here. So we plug in the fiber. We used, in this case, we used a 8 kilowatt laser, and we have an area where we put in our diffractive optical element. And you can see here, if we have the normal beam shape, so without the diffractive optical element, you can see here in the area of the focus spot, we have like a top hat or at least a super Gaussian profile. Whereas if we go, if we detune, so if we go to like here -4 millimeter from the focal point, we go more and more for a Gaussian profile. We tested the mean power that our self-manufactured DOEs could withstand, and found out that 4.5 kilowatts is okay for the DOEs after that. So with higher power, unfortunately they are destroyed, but for powder bed fusion, this is quite okay for us. So the smallest structure due to the optical setup is 110 micrometer that we can reach. As you can see here, we do not have speckles because we have a multimode laser, which is quite fine for us. If we have now the light source, the next thing is how do we do our first experiment. So we didn't do this in a real machine. Why? Because it's so let's say the means that you have to put in high-speed cameras and so on in a real machine are quite limited. And of course we wanted to see our process. So this is why we made a moving process chamber that you can see here. And this is the technical drawing here. So we have a substrate. We can have a definite layer of powder or a defined layer of powder thickness on the substrate if we want it. And we have gas in here, so we can control the atmosphere. And this is the glass where our laser shines through. Interestingly, what we do is we move the process chamber, whereas our laser setup and the camera setups and everything is fixed, which allows us, let's say, the best sensing technology that we can have here, because we use 2 high-speed cameras with up to 100 kilohertz each. The material that we did the investigation, this is something we are interested in a collaborative research center 814 funded by German Research Foundation, is an aluminum copper rod alloy, which is normally not for melting because it's no cast alloy. Anyway, we have the idea that you can use it for additive manufacturing, and already prove it that it can work. So we do our experiments with this material. As I already mentioned, the static position of the laser spot allows also static observation with the 2 high-speed cameras from different angles and gives the best images. So some of the first beam shapes we tried was the ring shape, as you can see here. You can see here the intensity. A line shape, so which is connected dots, and a point line, so which is non-connected dots, to allow let's say an area always between the 2 points that is not influenced by the laser beam. So you can see here we have quite a low peak intensity, as you can see here also from the light violet color, whereas here on the right side we have the highest peak intensity, so which makes this beam shape prone to material vaporization. Well, we wanted to see how those behave in a real process. So of course we started with a powder layer first because we want to go for additive, but we found it quite hard, as you can see from this video here, to estimate, for example, the actual size of the molten pool, because it seems the molten pool already moves forward below the powder that you can see here. So as you can see, the powder goes in and then drops in the molten zone. So this is not so easy to see what's going on here. By the way, this is the ring shape, as you can see here from the picture in the upper left image of the high-speed video. So what we did then, is to see the first, let's say, process change in the laser material interaction. We didn't use powder, we just used a pure metal plate, and you can see what's going on here. Again, with a ring shape. The dark black areas here show that we broke the oxide layer and we had molten. We really were able to melt the oxide. And here it's quite easy to see which area is molten and which not. What you already can see from both ones, it seems with a ring shape, this is a real calm process, so no big process dynamics here, no spatters at all. I will come back to that one later. So looking here, what's the influence of the different intensity distributions on the molten pool shape? You can see it here, and we tried also in the orange dotted line to show you how is the solidification front looking like. And you can see that depending on the intensity distribution that you use, we have quite different shapes of the solidification line, which of course influence not only the microstructure but also things like hot cracking susceptibility, for example. And this is shown here. Of course also the flow of the molten material is influenced, and I can show you this here in a few examples. On the left side, again, you see the heat conduction mode welding of the ring shape, which is really not big dynamics, so it's really calm. The molten pool is really calm here. Here we use the defocus, but with process parameters that are in between heat conduction mode and depenetration mode welding. So this is what we call transition mode. Of course, we do not want to go into keyhole welding. So and this is the early phase of the transition, so we are nearer to the heat conduction. And you can see there's some significant waves running here back, and there is some higher process dynamics that you can see here. So I have to restart. Let me try to do this once again. I'm sorry. No, it's not starting, so just a second. I think I can start it here. So this is with a little bit higher line energy, as you can see here, from 6.5 joule per millimeter to 13 joule per millimeter, again with a defocus. And you see that the dynamics getting higher, whereas here with a dotted line, so with the single dots, we already have keyholing here, and you see spatters coming out of the material. Even though this is still not powder, this is still the metal material. So, as in general, we can draw the conclusion that on this side we have the better process stability, whereas when we go to the right side, process stability decreases and melt pool dynamics and vaporization increases. Of course, we want to be always in between. It's easy to say, okay, then we use a defocus and have just less line energy, and then we are not in the transition mode but remain in the heat conduction mode, but then we are slow. And productivity is one of the main things that needs to be increased in additive manufacturing. So we had a look at the process windows, and what you can see here on the right side, you can see here in this diagram on the upper side, it's the TMW, which is the transition mode welding, so the transition to keyholing, whereas here on the lower area we have the heat conduction mode welding. And the lines here represent for each intensity distribution the borderline between heat conduction mode and transition mode. And as you can see here, so the line shape at first changes with the lowest powers, changes to transition mode, whereas later on we get the point line, and then also the defocus changes. What you can see also here with the peak intensity, so here measured as peak intensity, we have again the line here. Then we have the different points, and then we have the defocus. So let's say the general behavior is roughly the same. Defocus and the pointed line, the point line have quite similar thresholds, whereas the line has a significantly lower threshold, especially when we compare the peak intensities, not only the power. For the ring shape, you would maybe mind that you don't see the ring shape here. This is the reason because for the ring shape we were not able to leave heat conduction mode. So with the ring shape we never came into transition mode. You might have estimated this because this has the lowest intensity of all of them. But what this also shows is that the process window is very strongly influenced by the beam shape, and as soon as we are leaving intensity distributions like Gaussian or top hat, naming the peak intensity is no longer a good indicator for the processing regime. So as soon as we start with beam shaping, we need other parameters to describe what's going on. But this is only a side thing I wanted to say. So if you look at the welding cross sections, you can see here what happens with the ring shape. You can see here the line, and you can see here the dotted line, and these images show you the width over the power and the depth over the power. So the ring shape, the ring needs a higher power to even create a melt pool with a constant feed rate. Nevertheless, as it has a lower average molten pool size and molten pool surface temperature, it indicates always a more stable process. So the most stable process is always with the ring shape that you can see here, and you might have expected that, whereas the others behave different but not as good as we wanted. Something that might be also of interest is the surface after the weld that we had a look at. And you can see here again the best surface quality we reached was with the ring shape, whereas with the other ones like the dotted line, you can see here, so we have reduced quality of the surface because you always can see that we had small transitions into keyholing here where the dots were, where the middle of the dots were. With the line, you can see cracks that appear in the middle as well as with the defocus, which has to do with the shape of the area where you have solidification. So the shape of the solidification line, or the shape of the solidification area, to be more precise, is strongly connected to the growth of, for example, dendrites. And this again is connected to, do you have hot cracking or not? So also here we have a first indicator that with the different shapes, it's what we expected, that you even are able not only to have less spatter, but also that you are able to influence hot cracking behavior, which is quite good, by the way. Let me summarize what I just said. The DOEs, in general, they offer the possibility to investigate just a single optimized beam shape at a time, but already shows some good behavior. And on the right side, you see one example here that is done with a, let me call it an optimized beam profile for powder melting. It's not only a ring shape, but a ring shape with the two structures here. And interestingly, this is also the logo of my institute. We didn't know that before, because when we invented that logo, this was more like a bead in near field or so, or a bead trapped in a focus. Anyway, this is also quite good for additive manufacturing, it seems. We can influence, and we have seen this in the last minutes, the molten pool shape, also the cross-sectional molten area, the process window, and the surface quality by changing the intensity distribution. This also means we can use that also to avoid hot cracking. What we didn't do yet, and what is something we have to do and we will do in future, is that we can apply dynamic beam shaping to have some real-time control over our process, and also to find out what is the optimum beam shape depending on the current conditions of our process. With this, I'm at the end of my talk. Thank you very much for your kind attention. I hope that I could show you something interesting, and now I'm open for questions. Thank you.